Okay, good morning, good afternoon, and good evening, everyone. And welcome to the IES Day Women in IES webinars for celebrating our IES Day in 2024. So today we have two speakers, Dr. Chin Tan, who is a senior researcher from Interact South Korea, and Dr. Kristen Booth, who is an assistant professor from the University of South Carolina. So each seminar will take around 30 minutes plus 5 to 10 minutes question. This IES Day we planned in the society is from November 11th to December 6th, and with many events happening worldwide during this period. So for today's session, I'm going to introduce Dr. Kristen Booth first. Kristen is an assistant professor at the University of South Carolina and a joint appointee with Savannah River National Laboratory. She was a postdoc fellow at the Ohio State University in the Center of High Performance Power Electronics. And as an NSF graduate research fellow, Dr. Booth completed her PhD from North Carolina State University in 2019. Her research interests include resiliency and reliability of microgrids, AI integrated power electronics, and digital twins for grid modernization and security. So, Kristen, you have the floor, and thank you for your contribution to IES Society.
Thank you so much for inviting me. I'm looking forward to it. So today I want to spend some time discussing digital twin architectures and how they can be used for microgrids within industrial applications. So the very first thing that I want to highlight is where a digital twin, where the concept even began. So the thought process behind it is that it was born at NASA in the 1960s as a living model of the Apollo 13 mission. So the simulators that they originally used to train the astronauts were then switched over to a deployable asset that they could study some of the catastrophe that occurred during this mission and be able to prepare for the proper dark start procedures in a safe environment prior to deploying it to the astronauts who were in space. And so these simulators were the first digital twin because they were the first opportunity to study what was going on in that in situ in space in a bit more of a comfortable environment, and so that way the crew could be brought safely home. So the first thing that I want to point out is the National Academies of Science, Engineering, and Medicine recently developed this report on digital twins and some gaps in future directions that are required. I'm going to use their definition as the structure of this presentation today, as well as the measuring tool to determine what makes a digital twin a digital twin. Don't worry about the definition right at this moment. We'll go through it through the course of this discussion. And then by the end of it, hopefully you'll have a really good mindset of how digital twins can be used for industrial applications. The very first part of the definition that I want to go through is actually at the very end. And it's kind of interesting that the most critical aspect they highlighted, and they even say essential to the digital twin at the very end of their definition. So this brings us to, what is a digital twin? Is it just a model? And honestly, if you take anything else away from this particular presentation this morning, that you'll walk away and understand that a digital twin is not simply a high fidelity or any level of fidelity model. So this is a paper that was published last fall that I'm referencing here. They did a really nice job of doing a meta-analysis of over 200 publications, and they started to fit them into these categories of building up these different tiers of what could be what's required for a digital twin. So on the left side, they have all of the simulating capabilities that are required. So the basics of being able to represent the physical asset in the cyber, in the digital realm. And then on the right side is really more of the digital twin capabilities of being able to, merge with that data or age with the hardware over time, and really be synchronized and ultimately bi-directional with the system. An interesting outcome of this paper is that not a single paper that had described themselves as a digital twin was really capable of moving up these tiers to enhance both S4 and R4 relationship to be a digital twin. And I would fully agree with that in terms of the papers that I've seen in that time frame. So emphasis on this bidirectionality, I really want to focus on, what makes a digital twin, and this bidirectional communication is vital. So I came up with an analogy earlier this week. I'll try it again on you all, and you can tell me if you like it or not. What we like to think of, for example, is our own household budget. So I'm going to use our budget as an example. The digital model would be like taking your budget and just writing it out for the month, and potentially not looking at it again until the end of the month and saying, oh, well, I kind of followed this budget. The digital shadow, moving to something that has some communication, some information transferred, is that you have the budget that can, that as you purchase things over the course of the month, you go back in and fill out your budget and say, okay, I've used 50% of my grocery budget this month so far, and I'm 2 weeks into the month. Okay, so far so good. But finally, moving to a digital twin of our budget is not only are we taking this information and understanding how much we have left, but for example, let's say I overspend in my grocery budget for this particular month. Now I have to make a determination of where can I cut elsewhere in my budget in order to stay on task. So that might be, reducing my shoe budget, because I personally am a big fan of shoes. So I have to switch that out so that I can purchase the groceries that I need for the following week. So through our research here at the University of South Carolina, we have been really focused on the architecture of the digital twin and how to interact and do this bidirectional communication. So through some funding from NASA, we set up this structure, and I'll now go through all of it in detail so that you can get a good understanding of what we're doing with how the structure functions. So the first thing that we want to point out is the physical twin. This is, the vitally important aspect of our digital twin structure here, because unless you have to have something physical in order to study it and to do what you need to do to create a digital twin. So it's the physical asset under study. It can be extremely complex in terms of an entire industrial complex, or it can be as small as a single robot, or even into the subcomponents of the robot itself. So I just wanted to put this example up here of what we could see a future microgrid that looks what it could look like at an industrial facility. So we might have electrical trucks coming in and needing to be charged while they're getting reloaded. We'll have energy storage. We might have some distributed energy resources such as wind or solar. There's Internet of Things sensors all around. So we have lots and lots of components that require energy, and we need to make sure that we manage this energy in an efficient way and an optimal way for the industry complex to be able to do everything that it needs to do to serve its products to the community. The next thing I want to highlight is that digital twin component. We really like to focus on calling it the faithful representation of the physical asset. It can be one or multidimensional. It can have a variety of representation features, which I'll talk about shortly. And a key structure that I think makes it go beyond just a simple model is that we need to be able to enable early raw data analysis inside this digital twin to make it very easy to move up the structure and to make decisions. But at the end of the day, if you create an input, and ideally it would be an input that you would see in the physical twin, that both of them will have the exact same response. So moving up the ladder, we have the decision maker. What we think is really interesting about this is that it can be completely autonomous. It can be a technical operator or any sort of human in the loop. So ideally, it doesn't require an expertise in order to function in this structure. And the key aspect of the decision maker is that it can request a specific type of response, and it wants to study several different versions of that response to determine what's the best way to control the physical twin. So it's really an outermost loop control for the system. And as you can see in this figure, it derives and sends instructions to the physical twin, which, like I said, can be autonomous or human in the loop. And ultimately, in order to do all of this, it really needs the query and response, call and response of the structure to send information to the digital twin and to get a response back to determine what to do about it. So just to highlight the query and response components, the query is to say, hey, we want to see what's going to come down the pipeline. We have a truck coming into the complex we need to charge. We also know that we have certain products that are currently with the, on the conveyor belt that we need to make sure get transferred down the system. And so we've got all these things going on. How am I going to do it? And so that's this query and response loop that can happen. So we take conditions that we see initialized in the physical twin, we send those up to the digital twin, and then the decision maker says, I know what's coming into the future, so let me go ahead and add that to the mix. And I'm going to ask the digital twin to forecast and project what are some options we can do in order to supply all the loads that are demanding right now. And then the response will return back to the decision maker, which will help us enable that decision and send those instructions to the physical twin. The last thing that I want to point out is the physical system, which we want to encompass the entirety of this architecture. The reason why we want to explicitly call out the physical system is because we need to talk about the computing devices that are required to make all of this happen. So if you recall from my previous slide, we had a data center inherent to the industrial complex. That could potentially be a piece of equipment that is located internal to the structure, or could be potentially cloud computing. And so we want to make sure that we understand that the physical location of that doesn't matter, but you still have to encompass that into your system. It can also be on the edge devices, especially because all of our robotics have controllers inherent to the systems that, depending on your resources in that microcontroller, you might be able to also incorporate your digital twin on the edge as well. Okay, so now that we've talked about the bidirectional interactions, the next key component is that virtual information construct. So that's where we always talk about that faithful representation. And like I said earlier, I really try to avoid saying it's a model. And the reason why I say that is because there's a variety of techniques that we can use inside this digital twin faithful representation. It can be simulation-based modeling, physics-based, data-driven, so we can have some artificial intelligence in here, or it can be a hybrid of any of those types of techniques. And I think that we're very familiar with that realm of being able to represent in the digital structure, so I didn't want to spend a whole lot of time on it. The next aspect, which is also very similar to that simulation realm, is that we need to mimic the structure and the behavior of the system. So I wanted to point out just a little bit of work we've done in this area. And like I said, this is very similar to what we're very accustomed to in terms of let's do a simulation, and then we'll do it in the hardware and we'll push through, right? We want to make sure that we have a good comparison. But the key difference between those two aspects is that we actually have, like you can see in this figure, the digital twin active in the communication of measuring some measuring some conditions in the physical twin and updating it as it goes. So in this particular example, we're going to do a digital shadow. So it's going to take instantaneous measurements from the digital twin, and then it's going to use that information to show a response that would then go to the decision maker. So in this particular example, it's a very simple converter topology, and we're measuring voltage and currents, which are being accessible to the digital twin. Here's a figure of our particular experimental setup that we used for this. And we did a couple of different scenarios just to show that the digital twin is having that mimicking structure no matter what kind of loads were being produced for that scenario. And so ideally what you end up seeing is this really nice, beautiful overlap of the physical twins responses as well as the digital twins responses based on that input information, which you can see here. I wanted to point out that this is digital twins are not just a single domain, that they can be an interaction of multiple domains. And so we used a very similar procedure, and we were doing some thermal mimicry as well. And in this particular, we'll use this example for another aspect in the forecasting that's required of digital twins here later in the presentation. But that the thermal mimicry here, we just wanted to show a couple of different power demand structures and how the thermal mimicry also aligns very well. So we have just a base load here on the left side, and then on the right side, we've integrated some pulse power demand. And this is, of course, a very long-term study for the thermal management. Now that we have those aspects, the next key important feature that differentiates digital twins from things that we're familiar with in the simulation realm is the ability to dynamically update with data from the physical twin. So what do I mean by that? What I mean is that as the physical asset ages, the digital twin should also age to represent what's going on in that physical system. So here's a couple of examples that I wanted to put for digital twins if you are having a product that you are producing and sharing out and selling to consumers, that particular product will likely have tolerances. And so if you were to sell a digital twin with that particular product, you would likely only develop one, and then you would want each one to basically individualize with the usage case that that individual product ultimately sees. So for example, if I have company A and I'm selling batteries to several different companies for other applications, one company might choose to use that battery at a near constant power. It's always in use. And maybe company C is using it sporadically just for load fluctuations. And so based on those different use cases, as well as calendar aging for a battery, for example, we want to see the digital twin individualize over time. So they start with the same structure, and then they would change with the use case that they see. So there's a couple of different methods of tuning. At the end of the day, it relies on historical data. So it will tend to have some sort of hybrid modeling of artificial intelligence with physics-based modeling to produce this. And then with that capability, we can also keep in mind, predictive maintenance, remaining useful life, stability for your microgrid, limits of your operation, for example. So there's a lot of different things we can do once we know how our system is really being affected in that particular example. So I just wanted to point out one particular bit of research that we did where we talked about this kind of tolerance perspective. We knew basically what was inside the box, but there's minor variation in all of the equipment. So on the left-hand side, you can see the before fitting of the physical twin and digital twin in terms of responses. And then after that, we were able to show when we did the digital twin tuning that we can create a very similar response in the digital twin as identical to the physical twin responses. Okay. Finally, a really unique feature of digital twins is the predictive capability. And I really like how they put in this particular definition that you can inform decisions that realize value. So it's very application specific. What do you want out of your digital twin? So from an industrial application perspective, what product needs to go out right now versus what product maybe needs to go out in a month. So which equipment needs to be running, but we have to, we don't want to have that last minute run to the gates on the next product that comes through. We want to make sure that everything's kind of well prepared and well aligned to make it through our complex off to production. So right now we have a very simplified forecasting projection example, and this is where we get drastically different from what I showed earlier with the mimicry, right? We're actually wanting to forecast in the future what's going to happen if. So this happens to be that thermal digital twin that I was talking about earlier. We're bringing it back around here again. So this is all thermal representations. And the reason why this particular figure kind of looks a little bit out of place is because we're actually talking about projected measurements in time. So for example, let's take data point B. There's been a change in current demand for this particular physical twin. And so we've updated our forecast of digital twin. So the forecast is actually that initial data point, that black dot. And if you can see that, I like to talk about it as a dot dash. So if you see the dash that is aligned with that dot, that's what we expect to happen in 3 minutes from now. So that line is actually the time differential between what we projected and when it actually occurs. So this is a completely simulated with no non-idealities. So this is a perfect conditions. So as we see this dot dash, you can see that we're doing a thermal representation that in this particular point at point B, we have a forecasting window of 3 minutes, and we can modify that forecasting window based on our interest, right? That'll be a key aspect here in this example. So this particular work was funded by NASA, by Navy, ONR. And so this is a ship microgrid representation. And what we wanted to talk about was, for example, if we want to manage a particular cable, and this is arbitrary values, but this is just kind of a simple example of showing how we can forecast and project. So I want to keep this particular transmission line within a specific temperature set, so that way, if because there's a high criticality, something down the line that needs to maintain the capability to receive and transmit power. And so we really wanted to focus on, can we keep that particular those temperature requirements in play? Excuse me. And so through all of this, so that's our objective. Our decision maker helps us decide what our forecasting window are and is in our constraints. And then based on this, we used a resistive droop control method to be able to modify what was going on in our miniature power system to make sure that we can regulate that temperature properly. And through all of this, our digital twin was able to forecast and make sure that we maintain those constraints. And the way that it did it was sent us a warning flag. And then that warning flag also came with a countdown so that we knew exactly when our constraint would be exceeded. So here's an example of in situ how this would show up. So for example, we've got our forecasting data point, that is that black dot, and you can see our dot dash occurring again. We also have the instantaneous data coming from the physical twin, so that's the red line here that's growing with time here at close to 24 degrees. And then you can also see our temperature constraint boundaries, the red horizontal dash line and the green horizontal dash line showing our upper and lower boundaries respectively. And so what happens is as soon as we start our hardware, you can see the hardware temperature starting to increase, and you can also see what we expect to happen 2 minutes from now in this particular slide of where the temperature, we expect the temperature to be. And so in this particular instance, we have a 2-minute forecast, and we're showing that we're within those constraint boundaries. And so we're not going to change anything about the hardware in this instance. Now we're going to only run the digital twin every minute. So the very next time that you see it is at 1 minute. And you can see that our forecast is also showing that we're staying within those constraints. And so we're not going to take any particular action. Once we hit the 2-minute mark, you can see that our forecast has exceeded the constraint that we've expected. Now, excuse me, in this particular example, we didn't have a complex autonomous decision maker involved. And so what we did was a very simplified control system. We know that we're going to exceed this value, so we're going to wait for 40 seconds, and then we're going to reduce the load on that transmission cable. And so you can see our action is we reduce the load, and you can see the temperature starting to fall. But we're not at the 3 minutes, so we haven't done an update on our digital twin at this point. At 3 minutes, we do that update, and you'd see our temperature is going to be forecasted to be below our lower constraint. And so we're going to make another change to the system now. So we're going to wait 60 seconds, and then we're going to increase the load. Like I said, all of the controls here are very arbitrary. We're just managing this in a very simple decision maker structure, but this can become much more complex so that you don't see this oscillation that you see in these particular slides. And so as you can see, we can maintain between those constraints that we provided there. So at this point, we've been able to show the entirety of a digital twin requirements. As you can see, we've done individual aspects in, at least in my team, where we've spent some time in each of those components of that definition. There's a lot more complexity to it, but I really want to keep it high level for this talk. But I wanted to show just kind of overall where this is going and why digital twins are even relevant to the industrial applications. And as you can see here, in terms of the applications and the global digital twin market, in 2023, it was estimated to be almost $17 billion. And they're expecting this growth in digital twins about 30% every single year, at least through 2030 that I've seen recently. And as you can see here, manufacturing takes the second largest chunk of this market right now, and it's only projected to continue growing, especially with the Industrial Revolution 4.0. Because I'm a power person specifically, I focus on the applications in power. So as you can see, there are several different companies, different research groups, all involved with digital twins for the grid. As far as the companies go, they tend to talk about their digital twin being a very high fidelity representation of their grids. They don't necessarily have that bidirectional communication feature that is so integral to digital twins right now, but it looks like they're trying to move in that direction. But this is definitely something that, even though it's a very hot topic right now, it's going to take a few years for the companies to really get all of the key aspects of the digital twin that we just discussed in this particular conversation. But as far as what we expect from digital twins and the impact that they have, GE Vernova just published this on their webpage, that they were able to save over $1.5 billion in terms of operations and maintenance. And so just based on, this one particular company, as well as the capabilities that the predictive maintenance and all of that comes into play, especially when you think about, any sort of unexpected maintenance that you have to shut down your system for, right? If we can predict that and be prepared for it, you can keep all of your operations running in time the way you want it to be. So we project to see a lot of economic benefits to having digital twins with any particular piece of equipment. There are some challenges with digital twins, and I'm just going to highlight them very quickly. I'll go clockwise from the top. The real key challenge is high quality data coming from your physical twin. If your sensor measurements are not calibrated, if there's noise, anything like that you can't filter out, but you don't want to over filter so that you don't have too much of an average, you've really got to balance the demands of your needs versus the data that you need there. There's some issues with data security, right? From an industrial perspective, the company wants to keep their IP very private. They don't want people to know what's running for what productions, et cetera, et cetera. So we want to make sure that digital twins can be used for that. And I think that they can, especially in the cybersecurity realm, as a potential honeypot for potential intruders. There's also a very high cost for implementation. You've got to have the expertise. You have to have the understanding of the equipment, which is purchased from multiple different companies. So that can be a problem unless the companies produce the digital twins for you, so that you have that, maybe it's a black box that you don't really have access into, but you could use in your own digital twin. Which brings us to the last challenge of the complexities of data integration. If you have multiple different products from multiple different vendors all being used in your facility, you have to be able to crosstalk amongst all of those so that way you can provide these benefits that we're seeing with digital twins. Specifically in terms of microgrids, I think that they're very useful for us to be able to prepare for any impending disaster or recovery from disaster. They're ideal for energy management, being able to predict in the future what do I need versus what energy do I have on site. If you have renewables that you want to integrate to your facility, it will really help enhance your local grid stability, and then of course reduce the reliance on transmission lines with distances to their to like a fossil fuel based energy production location, so that way you don't have to worry about anything that happens in weather events or otherwise that are in between you and your energy resource. And then finally, an interesting concept with digital twins that are really exciting from a workforce development perspective is that you can actually train your workforce based on your digital twin, through the historical data that you gather from your facility. So if you know that you want specific outcomes based on previous experiences, right? That engineering mindset of the understanding of what's going on, you can actually train that into your workforce, even if maybe they don't have that same expertise that you have, so that way they can see actually what's already happened in your facility before and then know how to handle it in the future before they actually are ever operating or maintaining your facility. There is some standardization. I don't want to go too much over because I'm a little bit over time as it is. But we have some manufacturing standardization that's going on. That'd be ISO 23. I can't remember it off the top of my head. Let's see if I can find it really quick. No. There is some standardization going on, but there's some key aspects that we need to think about in our future, and that's especially in interoperability, for, like I said, the different components, the robotics, the Internet of Things, all of those things need to work together, and so we have to think about that communication and requirements there. We want to have a very consistent framework for developing and deploying digital twins. So that's why I harp so much on the architecture itself, to make sure that we're all on the same page of exactly what they're going to do and how they're going to do it. And then, of course, there's a scalability aspect to it as well. That we want to make sure that everything that we do can, as your facility grows, right? You might create a new line in your facility. You want to be able to make sure that that new line can be physically implemented, as well as in the cyber physical space of your digital twin being implemented as well. I just want to point this out that we have a microgrid lab at the University of South Carolina. On the left-hand side of this figure, you can see that we have a DC microgrid. It's actually moving towards an AC DC hybrid grid at the moment, that we can do all of these tests on. We think that it's vitally important to have the hardware, the physical twin actually in hardware, to show the capabilities of your digital twin. So that's one of the key things that we're looking at here. So this particular facility on the main test bed can do about 300 kilowatts of power. And then as you see on the right-hand side, we also have de-risking stations, as well as our computing resources in the operation area. The de-risking station can do about, right now we're setting up a test for about 50 kilowatts. So we can really look at this at a much larger scale than just that smaller single converter 10 kilowatt perspective. And so it's really important to be able to see larger scale of systems working together with your digital twin. So with that, I believe that's my last slide. I wanted to do a shout out to my recent graduate who did a lot of this research. And I'll take any questions.
Thank you, Kristen, for this wonderful talk on the digital twin. So now let's open the floor for questions. Let me stop the video now.